Well, we may get started. We just have one lesson this week. We've kind of slowed down now that we've hit these rational expressions. I know that a lot of people aren't comfortable with fractions, and then when we take equations and put them into fractions, take expressions like polynomial expressions and put them in fractions. People go, "What?" So we're kind of taking it slow and going through. Let's see, what did we do last time? We talked about what my notes discontinuities, right? We were finding holes in graphs last time. Yes, I have those notes here. We had holes in graphs, and I really need to clarify because I did not do a good job of really explaining the difference. This week we're going to study asymptotes, and we're going to start with asymptotes. You're like, wait a minute, what's the difference between this and holes? Well, I mean, it's an obvious difference when graphing, but how can we look at the equation and see there's a difference? Because I really didn't do that well last week in retrospect. So we're gonna kind of clean up last week's lesson at the same time and getting into this week's, because they're very, very similar as far as numbers that x can't be, based on a lot of the same things. So we'll get into that. So let me put up our window here, our class in Buzz. We go to our grade screen. Let's go down, 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 past all these matrices. We are down at 6.03 asymptotes of rational functions. And next week, we'll actually solve some rational functions. We haven't solved any yet. Well, we've been simplifying. We've been having discontinuities. This week, we'll have asymptotes. And then we'll have solving next week. But 6.03, so let's switch over to that. Let's see. When you were in elementary school, you learned about latitude and longitude, right? The imaginary horizontal and vertical lines which circle our globe. And at the time, these lines might have not seemed very important to you, just something else you saw on the globe. But now you can imagine how important these lines are to airline pilots. They use these lines to navigate and determine their locations in the sky. Imaginary lines are also used for the borders of cities and states and countries. And while we may not be able to see these lines drawn along the ground, they are incredibly important. I mean, think about a military pilot. If a pilot were to cross the border from South Korea into North Korea without permission of the North Korean government, that could be an international incident because, stuff would start happening. Imaginary lines that the graph of a function or an equation approaches more and more closely are called asymptotes. An imaginary line that the graph of a function approaches more and more closely. So they defined it the same way they just used it in the sentence. Let's take a look. So we're going to learn about in what ways can vertical and horizontal asymptotes be identified in rational functions. Let's go to page 2. So vertical asymptotes. So if an asymptote is an imaginary line running alongside the graph in a rational function, then a vertical asymptote must be one of these lines which continues forever up and down. Let's look at this. This is the equation 1 over x, which is a rational function, 1 over x. And you'll notice it has actually 2 asymptotes. It never touches the y-axis. It never touches the x-axis. So there's asymptotes at y equals 0 and x equals 0. So unlike graphs of linear, quadratic, and polynomial functions, the graphs of rational functions often consist of multiple pieces due to asymptotes. So this has a piece in the first quadrant and a piece in the third quadrant, only 1 over x. Additional review on quadrants, if you need a little refresher on that. Quadrant 1, quadrant 2, quadrant 3, quadrant 4. You start up here with all positive numbers and you work counterclockwise as we number the quadrants, as we number the quadrants. So why does this happen? Since there's a variable in the denominator, 1 over x, the value of the denominator changes with respect to the change in the variable. Remember, as the denominator of a fraction gets closer and closer to 0, the value of the fraction increases. right? Because 1 over 8 is just 1/8, as shown in this little pie graph. If we make that number smaller and make it a 4, 1 over 4 is larger than 1 over 8. If we make it a 2, it's larger still. Now it's 1/2 of that. And so if we look closer at this graph of 1 over x, if it goes to 1 over 1, it's 1. If it gets smaller than 1, the graph is getting much larger. We went from 1/8 to 1/4 to 1/2 to 1 to it goes much, much larger as it gets bigger. And let's look at that on Desmos, because we're going to use Desmos today as we graph these things. 1 over x. Oh, I put 2 x's. Let's get rid of an x. 1 over x. There it is. So, it was 8, it was 0.25 or 1/8. And then it got to 1/4 when it was 4. And it got to 1/2 when it was 2. Where's 2? Come on, 2. There it is, 1/2. But the smaller the denominator gets, that x, the larger the value. See, it's 20, 21, 22, 23, 24. The smaller that x gets. But it will never get to be 0. So this will never touch this axis, because the x will never get to be 0, because 1 divided by 0 doesn't exist. You can't divide by 0. But even if that gets to be, x gets to be, and see, as this way, as x gets larger, the value gets smaller as it gets closer and closer to 0. But even if x is 1,000,000, 1 divided by 1,000,000 is not 0. It's just going to be a very, very small number. 1 divided by 18 trillion is still not 0, but it's going to be really, really close. So we see that asymptote, the two asymptotes actually, horizontal and vertical. All right. So the vertical asymptote is a line created by a restriction on the variable. And by setting the denominator equal to 0, you will not only find the restrictions on the variable, but also the vertical asymptote. Any function never intersects its vertical asymptote. So we'll have a little video here where he's going to talk about a horizontal and a vertical asymptote. And I want to kind of make that clear. I want to talk a little bit about on paper here first. I want to pull this up because he's going to talk about this equation of x minus 2 over x squared minus 4. And we talked about last week, we'd have a hole in the graph, and we were looking primarily at the denominator. What number would make that 0, right? And this has x squared minus 4 as the denominator. So anything that would make x squared minus 4 0 is going to be a problem. Our graph cannot exist at those places. Why are you not focusing? Come on, focus. There we go. So if we solve that, x squared equals 4, you got to take the square root of both sides. So x could either be 2 or negative 2. Right? And as we looked last week, we said, oh, that would be holes in the graph. Not necessarily. I didn't define that well because we were only looking at holes. We can factor x squared minus 4 to be x minus 2 and x plus 2. All right, that's what that factors to. X minus 2 cancels out with that one. So x minus 2, where x equals 2 at, is a hole. It's only a hole if it cancels out with part of the numerator. Over here, the x plus 2, which creates a problem at negative 2, this is an asymptote. I didn't really make that distinction last week. We were looking at the denominator. You have to figure out what cancels out. Since it cancels out, that's a hole. This one does not cancel out with the numerator, but it is in the denominator. So x of negative 2 would make this 0. That's going to be an asymptote when you graph it. So he's going to talk about that in this video. So we'll we'll take a look at this.
We're going to look at how to find the asymptotes in a rational function, that is, one that's in the form of a ratio or a fraction. Now first we're going to find our horizontal asymptote. For that, all we need to look at is the degree of the numerator versus the degree of the denominator. And we have three cases that can occur. We can either have a higher degree on the top, an equal degree top and bottom, or a higher degree on the bottom. If we have a higher degree on the top, what happens is that highest degree term is going to grow the fastest of all the terms in the fraction. So the top of the fraction is going to grow larger faster than the bottom of the fraction. So as the top gets larger in relation to the bottom, the fraction is going to grow larger and larger and larger forever. So it's never going to approach any particular value. It's simply going to increase without bound. So there will be no horizontal asymptote if you have a larger degree on the top. If you have an equal degree top and bottom, our largest two terms, top and bottom, are going to sort of outgrow everything else in the fraction. And so our ratio is going to approach the ratio of those two terms. So our asymptote is the ratio of our two leading coefficients. Now, as we have in this case, the degree is higher on the bottom. So what's going to happen here? Well, the bottom of our fraction is going to grow larger, faster than the top of the fraction. So in that case, the value of the fraction is going to get smaller and smaller. In fact, it's going to get teeny tiny after a while. It's going to begin to approach 0. So in this case, our horizontal asymptote is simply y equals 0 or the x-axis. Now what about our vertical asymptotes? Well, those are going to occur where there's discontinuities in the function, and those are generally where we have a 0 in the denominator. So let's factor this so we can see better what's going to happen. Well, this is the difference of two perfect squares, so we'll factor easily into x plus 2 times x minus 2. Now we might be tempted to say that we have horizontal asymptotes at both of the zeros that are going to occur here, both at x equals 2 and at x equals negative 2. But what I see here is that we have a common factor in the top. And this is going to cause something a little different to happen. You see, you get an asymptote where you have a 0 in the denominator and a number in the numerator. And so as you approach that point, as the denominator gets closer and closer to 0, our value increases rapidly. And so that's why we have that line swoop up alongside our asymptote going off towards infinity.
Whenever you guys,
we're not going to have that happen.
Whenever you guys are
at x equals 2 because we have a common
you guys are
factor.
going to hear
The
this
numerator and the denominator are both going to approach 0 at the same time. We're looking at it another way. The only value that will give us 0 for these two factors is exactly 2. If we put in 2.01, they won't give us 0. They'll simply give us 0.01 and 0.01, and they'll cancel, and they'll just leave 1 over x plus 2 to give us our value for the function. If we put in 1.99999, as many 9s as you want to go, we would knock out 0 over 0. We'd get same number over same number, cancel, and they'll just leave us with whatever's happening with 1 over x plus 2. So in this case, we do not get a vertical asymptote. Instead, we get a hole, and that's going to occur at a value of x equals 2, because x minus 2 is a common factor top and bottom. Now, that leaves us with a factor of x plus 2 in the bottom, and that means that a value of x equals negative 2, the fraction will become undefined. We'll still have a number in the numerator, and so that gives us a vertical asymptote, and that is going to occur at x equals 2. Now, what about our domain? Well, for our domain, we have to take both these into account because they are both going to cause an undefined function, and so we can't have that occurring. So we need to leave both of those out. So our domain is going to be all reals except x is not equal to negative 2 or
I've never seen so much.
and that's how we find the asymptotes and the domain of our rational function.
So he talked about, oh, I'm sorry, I didn't mute my microphone during that. If you heard teachers talking in the background. He talked about not only the whole and the vertical asymptote, but a horizontal asymptote. Because when we graph this, let's graph that. What is x minus 2 divided by, oh, I got to put that in parentheses. If I don't put the x minus 2 in parentheses, it won't put the whole thing in parentheses. Divided by x squared, it won't put the whole thing in the numerator. See, we can see there's two asymptotes here. There's the vertical asymptote at -2, which he talked about. And there's also the horizontal asymptote at 0. And he did talk briefly about how to figure that out. But as we get into the lesson get more into the lesson, we're going to take some notes on how to figure out what is the vertical asymptote. So I don't want to ignore that, but we'll get more into that. So let's talk about again, if the denominator is a factor of the numerator, then the restriction represents a discontinuity or a hole, right? When we had x minus 2 canceling out with x minus 2, that created a hole. If we have 3x squared over x, you have an x and an x that will cancel each other out in the numerator and denominator, which means there's a hole at 0, 0, not an asymptote. So let's look at this example here. So we're going to get into a horizontal asymptote shortly, but to find the asymptote, we just find what makes the denominator equal 0. So if we subtract 3, x equals -3 will be an asymptote. That's going to be a vertical asymptote at x equals -3. There's only a 4 up here, so we know it's not going to cancel out and be a hole. There's not an x plus 3 in the numerator. So let's graph that and take a look at that asymptote. Will be a horizontal asymptote, but we haven't got to talking about that yet. But let's turn this one off for now. We'll come back and do this. And 4 divided by x minus 3. And we said there's an asymptote. Oh, x plus 3, not minus 3. Plus 3. And we said there's an asymptote at x equals -3. So you can see it there in purple that as it gets closer and closer, and I zoom out, up or down, it gets closer and closer to that asymptote. Let's go with the green one. It's closer and closer and closer to -3, but it'll never touch it. Same thing going the other direction up there. Start with the green one. It's going to get closer and closer to -3, but it'll never get to it. And there is a horizontal asymptote at 0. Like I said, we're about to get into that in just a moment here. This was the vertical asymptotes page. So example 2, let's look at example 2 here. So let's write that down. Okay, x minus 9 divided by x squared minus x minus 2. Well, this factors to be x minus 2, x plus 1. Because -2 times 1 gives us our -2. -2 plus 1 gives us our -1x. So this simplifies to x minus 9 over x minus 2, x plus 1. Now notice, nothing cancels out. Nothing cancels out. But both of these are going to create asymptotes. Wherever x minus 2 equals 0, or wherever x plus 1 equals 0, will be an asymptote. So this is x equals 2, and x equals -1. We'll have 2 asymptotes with this equation, which we can easily see when we graph that. So let me just close both of them, close that, close this. So instead of 4, we're going to put x minus 9 in the numerator. And then on the bottom, we'll put the original equation, x squared minus x minus 2. Okay. And we said there's an asymptote at both x equals 2. See, it gets really close to there, but it never touches that 2. And we also said there's one at x equals -1. So it makes a parabola type shape, but it never touches either 2 or -1. And then so this has got 3 pieces. The green graph there, I can turn these off. 3 pieces because of the asymptotes. It exists everywhere else except for when x equals 2 and x equals -1. And this is what the graph looks like. And it also has a horizontal asymptote at 0. It gets, this one's interesting because it actually goes above the zero and then starts coming back down towards it. Where this side just starts getting bigger and bigger, getting closer to zero. So sometimes these asymptotes do something a little funny because this one actually crosses over. See, it's below the zero here. It goes above the zero on this side. But as it goes farther and farther and farther, it starts going back down, getting closer and closer and closer to zero. Kind of weird, but that's how it works. So we recognize zero as a horizontal asymptote and 2 vertical asymptotes. So that's what we're looking at. We're looking at the denominator and figuring out where is the denominator becomes zero. And when it's equal to zero, that's an asymptote, unless it cancels out with a term in the numerator. Then it's a whole instead of an asymptote, like we looked at last week. So here's more on vertical asymptotes. Identify the vertical asymptote of x plus 7 divided by x minus 8. Well, it's not going to cancel out with anything. So wherever x minus 8, what x would make that 0? Well, obviously it's 8, because 8 minus 8 is 0. So the vertical asymptote is at x equals 8. So don't make that hard. You just identify what x's make that 0. And if it doesn't cancel out with the numerator, it's an asymptote. If it does, it's a whole. Either way, it's not part of the domain. But let's talk about horizontal asymptotes. Okay, so the horizontal asymptotes are really defined by the degree. Let's see, defined by degree of numerator and denominator. We'll say, what do we mean by that? The horizontal asymptotes are defined by the degree, and I'm going to highlight the word degree because that's what matters. The degree of the numerator and the denominator. All right, so if degree of, I'm just going to abbreviate it, numerator is less than degree of denominator, and I'm just going to abbreviate that. Horizontal asymptote equals y equals 0. So the horizontal asymptote will be where y equals 0, or the x-axis. And what do we mean by the degree? That means if I have x, I will say example, x to the third minus 1 over x to the fifth plus x plus 2. What is the degree of the numerator? The largest degree is the third. What's the degree of the denominator? The largest is the fifth. 3 is less than 5. So since there's an x to the fifth in the denominator, but only an x to the third, this is going to have a horizontal asymptote at y equals 0. Well, let's prove that to ourselves. Let's go back to here. We'll get rid of this. And I'm going to do x to the third. Oh, I got to put in parentheses. X to the third minus 1 divided by x to the fifth. Look, it's already made that x equals the y equals 0 as an asymptote, and then you finish the equation yet, plus 2. It's got a horizontal asymptote at 0. It comes above it again here on this side, but then it comes back down and approaches 0. There's a horizontal asymptote. Now there's a vertical asymptote at -1, due to how all that factors out. Because -1 to the 5th would be -1 plus a -1 plus 2. So -1 plus -1 would be -2 plus 2. So, but we see the horizontal asymptote is there. That's what I mean by the degree of the numerator is less than the degree of the denominator. All right, so what else could it be? How about degree of numerator greater than degree of denominator? All right, so here, less than, greater than. What happens then? No horizontal asymptote. It won't have one. Go back here and change this to x to the 7th up here on top, so it's larger in the numerator. Now look, there's not one. See, because this will go up, and this goes down. There's no horizontal asymptote. There's no value of y that it never touches. Now this piece over here looks a little funny, and that's due to a vertical asymptote that it's not touching. There's still a vertical asymptote, but we don't have a horizontal asymptote. We change this on the bottom to the 6th. Now it's x to the 7th over x to the 6th. Still, it's larger in the numerator, so there's no horizontal asymptote. We could take away the x to the 6th and just make it x plus 2. No horizontal asymptote. But if this suddenly becomes x to the 9th on the bottom, now we've got that horizontal asymptote of 0 again, because the denominator is larger. All right. So that leaves one more possibility, right? Degree of numerator equals degree of denominator. Horizontal asymptote is y equals the coefficient. The coefficient over the coefficient. You're like, what? For example, if this is 3x squared minus 1 over 5x squared plus x plus 2, the degree is the same on top and bottom. The largest exponent is a 2. So the horizontal asymptote is going to be at y equals, oh, let me get another highlighter here. The coefficients of those two x squareds. Horizontal asymptote at 3/5, because that's the coefficient, 3 over 5. Oh, let's take a look at that on the graph, 3/5. So let's get rid of this equation. Let's do that 3x squared minus 1. Squared minus 1. Let's put that in parentheses, so it'll all be on the numerator. All right. And then it's divided by, what did I say, 5x squared plus x plus 2. Oh, that does something. It dips down. But what is this approaching? This is approaching, getting closer and closer to 0.6. 0.6, which is 3/5, right? There it's right above 0.6. But as we go this way, it's coming down closer to 0.602, 0.6022, 0.601 when we get there. So it's getting closer and closer to 0.6, which is 3/5. On the right side, 0.594, 0.595, 0.596. So he's getting closer and closer to 0.6. 3/5 is the asymptote. Let's see, y equals 3/5. There's that asymptote line that it's getting closer and closer and closer and closer to. But it's not touching. There we go. So that's what we mean. And here it is, how have they written it, how they have written it in our lesson. The relationship between the degrees of the numerator and the denominator of the rational function and the horizontal asymptote. So if the degree of the numerator is smaller than the degree of the denominator, your asymptote is y equals 0. If they are the same, y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. And if the numerator is greater, there's no horizontal asymptote. So let's look at another equation here real quick. Just as an example, if we have f of x equals 4x to the third minus 2x squared over x to the third minus 1. When we look at that, we say, okay, what is the horizontal asymptote? Well, these are both x to the third. So we have to take the coefficients. What are the coefficients? This is 4. What's the coefficient here? That's 1. So it's y equals 4, because 4 over 1 is just 4, right? So we expect this to have a horizontal asymptote up at 4. And when x equals 1, 1 to the third is 1. There'll be a vertical asymptote at 1, x equals 1. So let's look at that. So this was 4x to the third. Oh, let's go put in parentheses. 4x to the third minus 2x squared. What are you doing? You're doing something weird here. There we go. Divided by. And we said the bottom was just x to the third minus 1. You see, we have this asymptote at x equals 1 right here. That's not going to touch, so it makes some weird things in here. But the horizontal asymptote was at y equals 4. We see that this one dips down below it, and then as it goes farther and farther, it approaches that line of y equals 4. The other direction, it starts down low, jumps up above it, and then comes back down, approaching y equals 4 from the other side. So yeah, sometimes even though it's a fraction between the two, this is a fraction of 4 over 1, which is just 4. That's where our horizontal asymptote falls, is at y equals 4. So identify the horizontal asymptote of f of x equals 1 over x. 1 over x. Well, let's see. The degree of the numerator and the degree of the denominator, we need to check. 1 over x. What is the degree of this compared to the degree of this? What is the degree of the numerator? Thought about that one? The degree of the denominator is 1, right? Because that's x to the first. What's the degree up here? It's x to the 0. Because we have no x's up here. There's no x in the numerator. So this is to the degree of 0. Because x to the 0 equals 1. So it's just 1 times x to the 0. This is 1x to the 0, which x to the 0 is just 1. So it's just whatever number's there. So 1 over x means the degree of the denominator is larger than the numerator. The degree of the denominator is larger than the degree of the numerator, so the horizontal asymptote is at y equals 0. One over x, 1 divided by x. There it is. Y equals 0 is the horizontal asymptote. And x equals 0 is the vertical asymptote. Yeah, so y equals 0 because the degree of the denominator is 1. The degree of the numerator is 0 because there's no x there. It's x to the 0 power. So 0x. All right, now it wants to identify the horizontal asymptote of 3x plus 8 over 2x minus 5. And it's going to do this in a video form for us. Make sure we can hear that. You look at that, see if you already know what it is before they show you. 3x plus 8 over 2x minus 5. See how long this is. 46 seconds. All right.
To learn about the horizontal asymptotes of this function, determine the degrees of the numerator and denominator. The degree of the numerator is 1. The degree of the denominator is 1. Since the degree of the numerator and denominator are the same, the horizontal asymptote is defined by the leading coefficients. The leading coefficient of the numerator is 3. And the leading coefficient of the denominator is 2. The horizontal asymptote is at y equals 3 over 2, or y equals 3 halves.
That's it. It is that simple. If they're the same, just take the coefficients of the largest exponent. Yeah, it's 3 halves. So you may have noticed that they're both just x to the first power, so they're equal in the degrees. So it's just take the coefficients. Identify the horizontal asymptote of this, x squared plus 5x minus 9 over x plus 1. Well, if we look at that, this is a second degree. The denominator is only first degree. So what do we do when the numerator is larger than the denominator? No horizontal asymptote, because this was second degree, this was first degree. By the way, put this in your notes however you understand. If you don't want to abbreviate, because you may not remember what that means later, don't abbreviate. You know, you can use numerator and denominator. Put however you need. Write your notes however it helps you to go back and look at them later and understand them. All right? Maybe you want to write it exactly how it is in our lesson. That's fine too. There is no horizontal asymptote. There's one more example. Identify the horizontal asymptote of 4x minus 7 over x minus 3. This is very much like the one I did just a minute ago. This is an x to the first. This is an x to the first. So it's a 4 over 1 fraction, or y equals 4 is going to be the horizontal asymptote. All right, here's the lesson summary. So this can summarize all your notes in one place. Asymptotes, they're imaginary lines. There's vertical asymptotes, and it's found by setting the denominator of a simplified function equal to 0 and solving for x. Now this said simplified function, because after you simplified it, you've already canceled out the numerator and denominator. You've already pulled the whole out if there is a whole. So you can just set the denominator of the simplified function equal to 0, and that will be your asymptote. And then here's that little chart. If you want to copy this chart, or if you have a printer, just print this chart, put it in your notes. There's how you tell the horizontal asymptote. It's not complicated. You just have to pay attention to the details. And the more you do it, the easier it gets, because you understand it more and more and more. But the degree of the numerator is smaller than the degree of the denominator. It's y equals 0. If it's larger than the degree in the denominator, there's not a horizontal asymptote. And if they're the same, you just look at the leading coefficients and set them up as a fraction. That's the whole lesson, because now they just give us some practice problems. Select the correct choice and select submit to see if you're correct. All right, so this one, and man, it's really small. Let's see if I can make it bigger. Not really. It doesn't get much bigger. We'll try. That's about as big as I can get it, guys. All right, so put this in the chat. Identify the vertical asymptote of, this is 3 divided by x. 3 divided by x. What is the vertical? This is the up and down. Vertical asymptote. This is not comparing the degree. Comparing the degree finds the horizontal asymptote. So the one where you simplify it and find anything that would make the denominator 0. So what's the answer? Is it x equals 0, x equals 3, x equals 0, and x equals 3, or none? See how well you've paid attention here. Daniel's got an answer for us. Anyone agree? Oh, Soraya agrees. Seth agrees. All right. I see lots of folks saying x equals 0, because for vertical, we just figure out what would make the denominator 0. Well, if the denominator is just x, it's when that x is 0. Yeah, that's absolutely right. Excellent. The graph is a vertical asymptote at any value of x that makes the denominator equal to 0 and thus undefined. Right, let's look at the next one. How about the vertical asymptote of this graph? They didn't give you the equation this time. They just gave you the graph. You should be able to look at a graph and say, oh, well, there's the vertical asymptote because it's not touching that point. It's just getting closer and closer. But the question is, do you know what's vertical and what's horizontal? Because there's a horizontal asymptote and a vertical, and that's really what they're trying to get you right there. Yeah. Vertical means up and down, and that would be at -5. Yes, x equals -5. And they kind of drew it in there for us. See how they give this one. Oh, this one they make you do some work. The vertical asymptote of this function, which means you have to factor this, x squared plus 3x minus 18. And once you find the two factors, do they convert to x equals -3 and +6, +3 and -6, or +3 and +6? Or it doesn't have any vertical asymptotes? Okay, I think we can eliminate that last one. This one has vertical asymptotes because there's going to be some value of x, or two values of x, that'll make that 0. So you need to factor it in the two numbers that multiply to be a -18, but add to be a +3. So it'll be x plus something, x minus something. And I'm guessing it's 3 and 6. If we want to be a +3x, so it must be x plus 6, x minus 3, because you need the positive number to be bigger than the negative number for this to be a positive middle term. So if it's x plus 6, x minus 3, the values of x, that would make that 0. X plus 6 would be -6 plus 6, right? X minus 3 would be 3 minus 3. Let's put that in there. Excellent. There we go. Now let's see. You try 2. Is this horizontal? This is what I want to see here. What is the horizontal asymptote of this function? This is the horizontal, the flat one, the one that goes left and right. one that follows the same direction as the x-axis. So what is it for this function? X plus 7 divided by x squared minus 3. No factoring needed with this one. This is where you compare the degree of the numerator to the degree of the denominator. Which one is bigger? Okay, Daniel says, oh, I guess you mean y equals 0, you put an x. These are all y's. Horizontal asymptotes are y's. Y equals 0. We have a first degree numerator and a second degree denominator. So the denominator is larger. The denominator is larger than the numerator, so it's y equals 0. Just had to refer to our chart. Y equals 0. Excellent. Because the degree of the numerator is smaller, there's a horizontal asymptote at 0 there. Get rid of that. All right, let's go to page number 2 here. Describe the horizontal asymptote of this graph. Oh, that's a pretty interesting one. Got to pay attention to the scale. This is not 1, 2, 3, 4, 5, 6, 7. This is 0.25, 0.5, 0.75, and 1. It's a little tricky. You got to pay attention to the scale. So this one, the horizontal asymptote, that as the farther this graph goes, closer and closer, left and right, the number it's getting closer to as it goes left and right, it's not 0. It's going up from that. It's not 1 because 1's way up here. It's y equals 0.25. Good job, Daniel. Getting closer and closer to 0.25 as it goes left and right. Submit. Excellent. Or 1/4. Okay, here's our third and final one here. Describe the horizontal asymptote of this function. X squared plus 1 divided by x. Is the asymptote of y equals 0, y equals 1, y equals 2, or none? Y equals 0, y equals 1, y equals 2, or none? Daniel says this has no horizontal asymptote. Well, what do we see? We see there's a second degree and a first degree. So the numerator is larger. The degree of the numerator is larger than the degree of the denominator. There is no horizontal asymptote. None. Excellent. Okay, let's shrink this back down so we can see more of our page again. All right, very good. There's one more page of practice problems. I'll leave those for you guys to work through. Activity 1, activity 2. Match the asymptote to the situation on the left, on the right. This is good. When does it equal 0? When is there not 1? And when is it the leading coefficient? Degree of the numerator is less than, the degree of the numerator is greater than, or they are the same. See if you can match those. That's a really good one. Activity 2, describe the vertical and horizontal asymptotes on the graph. What do I do? Click that? Oh, there you go. Yeah, so say what it is, and then you can click this to see if you're right. There's the graph, and it shows you the asymptotes. Describe the vertical and horizontal asymptotes of this function. And then you can click to see if you're right. And this function. All right, let's look at our assignment. Which equation represents the vertical asymptote of the graph? The vertical asymptote is which one of these equations? This is an important question, actually, because we can look at the graph, but do we know, is it x equals or y equals? That's important. X equals 12 and y equals 12 are two very different graphs. If you're not sure, go to Desmos and take a look at it. Oh, gosh, Mr. Brock, I'm not really sure. Let's see. Y equals 12 would be that. X equals 12 would be that. There's the green one, there's the purple one. Y equals 0 would be this x-axis. X equals 0 would be the red line on the y-axis. So it is very, very different. And it's important to make sure you know which is the vertical, which is the horizontal. Identify the vertical asymptotes of this. Obviously, it has something to do with a 5 and a 2, but which ones are positive, which ones are negative. Identify the vertical asymptotes of this. Identify the horizontal asymptote and the horizontal asymptote. So we have 2 horizontal, 2 vertical, and 1 which equation represents the vertical asymptote on this graph. And your questions may be different. Remember that. Remember that. Your questions may be different because it has a bank of questions it pulls from, so you may get different questions than what I show on the screen because it randomizes, which is good. So, all right, guys. 5 questions. If you got your notes on this, you shouldn't have any trouble with that if you pay attention to the horizontal asymptote, because that's where you need the notes until you get that good and memorized. But you should be able to have this done by the time the class period ends. We got 30 minutes left in class. We're done with the lesson, so I'm not gonna keep talking for half an hour because I've said everything that needs to be said this week. So I will free you up and give you the rest of the class to be done with this lesson. So you guys have a great week. This is a day on Friday. So I'll be here Wednesday and Friday if anyone needs any help, any assistance. I don't know if anyone's below 70 in this class. If you are, I'll see you Wednesday and Friday. But if there is, there's not very many because most of you guys are staying right on top of it. Got your grades over 70%. So have a great week, and I'll see you later.